Okay, so sorry about that. I had my external locked on the other side of the screen, so that's why I couldn't get it to move over. But now that I've gotten that figured out, we can keep moving along here and talk about how we specify this this model that we came up with in R through WinBUGS. So the first thing, which I talked about, is you need to install it. Then you load the library. And then, very similar to what we did theoretically here, the first thing you want to do is write down your model. And if you're doing this directly from within R, then you write it as a function. And the syntax is exactly the same as WinBUGS, so if you're used to using the WinBUGS software, that's some good news for you, because you don't have to learn a new syntax to specify your model and prior here. Okay, so when we're specifying the model, the first thing we do is we put the likelihood. And our likelihood in this case is simply the fact that we've got a normal distribution for each yj. We have a normal distribution for each yj with mean mu j and a precision tau. So for each of the j's in our 1 to capital J, and this capital J is something we specify later based on the data that we provide, we just simply say that the y of j is distributed according to a normal distribution with mean mu j and precision tau. Now we need to define what these mu j's are, because we haven't defined them yet, and we can do that in this same for loop. So we can define our mu j's right here. We can define them as alpha plus beta, which is what our model says they should be, alpha plus beta, times the centered data, which is xj minus x bar. And so here in the model, it's important to keep in mind what's the data and what's the parameters that you want to look at. So the data here is y, xj, x bar, which we also have to provide, and this capital J. So those are all things we need to provide. What are the things we're interested in here? We're interested in tau, and really alpha and beta. And so those are things that we want to monitor, and you'll see how we do that later. So now that we've specified this likelihood model fully, we specify our priors, our diffuse priors that we came up with. In the same way that we say our yj's are distributed normally, we can say the alphas and betas are distributed normally with mean 0 and precision equal to 1/1000th each, and tau is distributed according to a gamma distribution with these diffuse parameters. So another thing that we can specify in our model is if we want to monitor or print out any particular functions of the simulated values for these parameters. And we can do that by just simply adding a function within that gives the rules for computing the particular value that you're interested in monitoring. So now that the model's fully specified within an R function, notice that the model's within an R function here. That's important if you're doing this from within R. You can actually write your model in a separate file and then specify where that model file is later if you prefer to do it that way. But I like to keep my stuff together, so I think that writing the model from within your R script is a good thing to do. Now we need to specify the data that we're going to read in order to simulate the parameters from the posterior distributions. And we do that by specifying a list, just like in WinBUGS, where each of these parameter names, y, capital J, lowercase x, and x bar, all need to be specified. So we see that we can specify y here as 1, 3, 3, 3, 5, and x as 1, 2, 3, 4, 5. And that means that we've got 5 data values that we're going to use to simulate the posterior distributions through the likelihood and prior model. So j equals 5, obviously, right? And the mean of these, the first 5 numbers from 1 to 5 is 3. So we have to supply that also. But now all of our data will be supplied in the model, so it can use the data in order to derive those distributions of interest. So now we need to talk about what we're going to initialize our parameters that we're interested in and using in the model to. And here in the OpenBUGS tutorial, they just use 1. They initialize alpha to 1, beta to 1, and tau to 1. But you could use random number generators to specify those. Notice again that the inits is in a function, and that is important because the inits is actually a piece of code that is run very early on by OpenBUGS in order to start out the simulation of the chains. So now we can get our model output. Now that we've specified these 3 things, these are the 3 things you need. You need the model, you need the data, and you need the initialization values for your parameters. And we can now call the bugs function that's built into R2 OpenBUGS, give it the data that we defined, give it the initialization procedure that we provided, and give it a listing, a collection of the names of the parameters that we're interested in looking at. So remember that you need to tell it what you want it to give you back out within the actual statement here. We then just point it to the model model.file, which in this case isn't a file. It's actually an R object that we create earlier with our function above. And you tell it the number of chains and the number of iterations, and then it provides you with the output. So let's run all of this and verify that it works. So the model was accepted with no errors. Make sure you remember to load your library before you try to use these commands. And so now we have the model output in a variable called model output. And let me now remove the pad from the screen so you can see the R console more clearly. That was the wrong one. Okay. So as you can tell, it gives us our alpha, beta, and sigma, which are the parameters that we asked for. It tells us the mean and all these quantiles of the last 500 iterations because it discards the first 500 automatically. So we asked it to iterate 1,000 times, but it discarded the first 500. So these are the statistics for the posterior simulations of these 3 parameters based on the data that we supplied to our model. Now, if we want to do more sophisticated things with the actual simulated values for each of these, then we can get those directly by well, first of all, let's look at what all is contained within the model.output object that was created. Output. Okay, so it tells you all of the things that you tell it, like the number of chains, iterations, burn-in, etc. And then this is the one we're primarily interested in, which is the sims.matrix. And this gives us the simulations of alpha, beta, and sigma and deviance for each of the for all of the 500 simulations that it kept. So if we want to take a look at the dimensions of that, we would expect them to be uh, 4 by 500. Yes, so we have these 4 values, and there's 500 observations of them. So we can now look at things like, for instance, the the histogram of the simulated values of alpha, for instance. And let me put that on the screen so you can see it. And we can do things like go and take the kernel density smoother of this and plot that on here. And you can see that we can put a smoother on it and take a look at that. And if we had a more interesting posterior distribution, or if there was some bimodality exhibited, we could do some thresholding or something like that in order to find breakpoints, or all sorts of things you can do with just the data, the simulated data, if you can get it. And that's one of the powerful reasons why you should try and use OpenBUGS or WinBUGS through R, is so that you can directly interface with the simulated values after you're done with your modeling. So this has been a very basic introduction to using installing and using the OpenBUGS software to run a very simple linear regression model for some made-up data, and really just express what we are kind of trying to do with a Gibbs sampler and Bayesian modeling, and what it allows us to do and take a look at, and that kind of thing. I hope this was useful to you, and if you have any comments or feedback, feel free to leave that in the comment section below. Thanks. See ya.